So let me open up the chat. Of course, you guys have any questions along the way, feel free to either speak up or type in the chat, and hopefully I will see it. If not, I will get to it eventually. All right. So what we're going to do now is we're going to look at chapter 7, and we're going to start putting some of this stuff together and hopefully make some sense out of it. So there's only 2 sections here in chapter 7. The first one is talking about estimating a population proportion. Okay, so let's just talk about the notations and the assumptions, and then we'll see what we're actually trying to do here. Okay, so notations, these we've seen before. P is our population proportion. Okay, that's what we're going to be trying to estimate. Our p hat, which is x over n, we talked about that in chapter 5. That's our sample proportion. X is the number of successes, n is our sample size, and then q hat, which is 1 minus p hat, is the proportion of failure. So all that we've seen in chapter 5. And we also have some of the assumptions that we saw in chapter 5, along with a couple others here. We have an SRS, which is simple random sample. We always have to randomly select our participants. And then our binomial distribution conditions, those are what we saw in chapter 5. So the fixed number of trials, independent, meaning one outcome does not affect the outcome of the next one. There's 2 different outcomes, generally called success and failure, and then constant probabilities. And then the third assumption is that we have to have at least 5 successes and 5 failures in our trial. Okay, so let's talk about this point estimate, and then we're going to build from that. So the 2 we're going to cover today, and the only 2 we're going to cover, these first 2. And what we're talking about here is the point estimate. In this first section, we're trying to estimate the population proportion P. Okay, that's our true proportion. So let's just say we're trying to find the proportion of people that smoke marijuana in the United States. The only way we could find the exact value would be to sample every single person in the United States and find that percentage. That would take a lot of time, money, and effort. Okay, so generally we don't do that because, again, time, money, and effort. Okay, so generally P is unknown. What we do is we use P hat, which is our sample portion, to estimate P. P hat just comes from a sample. So for instance, if we sample 1,000 people around the United States to figure out how many of those 1,000 smoke marijuana, and maybe it's 490 of them smoke marijuana, our estimate would be 490 over 1,000, or just 0.49. Okay, so that would be our point estimate, and that would be approximation to P. Okay. Now, every time we do that, if we sample another 1,000 people, that 490 might be slightly lower or higher depending on that group of people. The same thing happens in the second one. X bar is our sample mean, and that would be a point estimate for our population mean mu. All right, now we're going to start putting this stuff together. I know it's not making sense yet, but give me a little time here. Now we need to talk about our critical value. Our critical value, let's go back a few chapters, and we talked about the empirical rule. We said within 1 standard deviation was approximately 68%, within 2 standard deviations approximately 95, and then 3 is 99.7. So that critical value is our cutoff score. We're going to use roughly 2. Okay, so if we say 2, that's our what the definition says is cutoff values that separate the sample statistics that are likely to occur from those that are unlikely to occur. So if we go to 2 standard deviations in either direction, or 2 standard errors, the chance that we're going to fall inside that region is 95%. Outside that region is 5%. So it's likely to occur inside 2 standard deviations, unlikely outside. Okay, we're going to adjust that cutoff value depending on how confident we want to be. If we want to be, approximately 95%, it's going to be really close to 2. If we want to be more confident, we're going to have to go out a little further, more like 2.5. If we want to be less confident, say 90, it'd be more like 1.6 or so. Right? So that critical value is this Z alpha over 2. That's our value, for lack of a better term, is our value of 2. Okay, I want to put that in quotes because that 2 is not exact, it's just approximate. So we're going to go out basically 2 standard errors or 2 standard deviations in either direction. So our margin of error is the 2. And the second part, the square root of p hat q hat n, is our standard error, which we've been calling standard deviation, but now it's called standard error. So this margin of error, we're going to find, go back up. We're going to start off with this p hat. Okay, that's our estimate for p. And from that p, we're going to add and subtract 2 standard errors. What that's going to do is it's going to build a net. And in that net, we're hoping to capture the true value of the population proportion p. Okay, so we're going to use our p hat, which is our sample portion, build this net. We're going to go 2 standard errors in either direction, build this net, and hopefully in that net we capture the true value of p. Okay, and that's what a confidence interval is, and that's what we have here. So we have our point estimate p hat. We're going to add and subtract. There's our plus or minus. Here's our 2, and here's our standard error. So we're taking our point estimate, we're adding and subtracting our 2 standard errors. So we're building that net. Okay. All right, now let me go up here and see if I can. Let's see. Okay, so this is a page out of the book. And this figure, we can kind of understand what we're trying to do and how this works. Okay, so what we're trying to do is we're trying to estimate the population proportion p. We generally don't know what that is. In this case, they tell us that p is equal to 50%. Okay, if we knew what p was, it would be silly to estimate it. So this is kind of unrealistic, but let's just pretend we had a magic wand and we know what the true value of p is. Okay. Now let's look at all these red and green bars to the right and see what those represent. Okay. So let's go back and say, okay, if we sample and we're trying to find our p hat, and say we sample 1,000 people. Okay. And out of those 1,000 people, let's see, we had maybe, that's not a very good 1,000 there. Maybe 495, let's just say 490 of them smoked marijuana. Okay. So that point estimate would be 0.49. Okay. So that's our point. Now, if we build a confidence interval around that, if we add and subtract 2 standard deviations, obviously I'm making these numbers up, but I'm just trying to emphasize what we're trying to do in general terms. We take our 0.49, if we add and subtract 2 standard deviations, say that's 0.02. Okay. Again, I'm just making these numbers up. So if we add and subtract 0.02 from 0.49, we'd have 0.47 on our lower end, 0.49 minus 0.02. And then our upper bound would be 0.51, 0.49 plus the 0.02. Okay. So we'd have that range. That's what this red bar represents. The lower end is 0.47, the upper end is 0.51. Use your imagination a little bit here. I'm kind of trying to wing it. That's what that first red bar represents, that confidence interval. Now, what we're trying to do is say, is that true value of p, 50%, in this region? And it absolutely is. It goes from 0.47 to 0.51. So yes, that would that the true value of p would be in that region. Now, the only thing that changes between that and the second red bar is our starting point. The next time we sampled 1,000 people, instead of having 490, looks like they had maybe 505 or something like that. Okay, so that changes our point estimate a little bit, and we still add and subtract the 0.02, and looks like we have a lower bound there, maybe at 0.48, maybe to 0.52, something like that, roughly. Okay. Well, is 50% in that range? Absolutely. And if we did it again, we're going to get a slightly different point estimate. We build our we go 2 standard deviations either direction. Does the true value fall in that? Yes. The fourth one, yes. Here, The green one, we got a bum sample. So what that means is when we sampled our 1,000 people, we only had about 450 of those smoked marijuana. So when we build our confidence interval, it did not capture the true value of P. Okay. So when we see all these red and green bars, if we were going to do this over and over again, sample 1,000 people, find our point estimate, build our confidence interval linear direction, build our net, most of the time we're going to capture the true value of P. Okay. Those represent all the red bars. Every once in a while, we're going to get a bad sample and we're going to get that green bar that does not capture true value of P. Now, what we're doing here is we're not going to do this over and over and over again. We're just going to do this one time. And in this case, they were building a 95% confidence interval. What that means, if we were going to do this over and over and over again, 95% of the times we did it, we're going to have one of the red bars. Okay, so almost always we have a red bar. Every once in a while, 5% of the time, we get a green bar. We only do it one time, and we say, okay, we're pretty confident we got a red bar and capture the true value of P. But we, never quite know if we got that green bar. Okay, so we can adjust that confidence level to whatever we want it to be, and what we say is we're fairly confident, 95% confident that the true value of P falls somewhere in that range. So in other words, we're pretty sure we got one of those red bars and not the green bar. Now let me hesitate there for a second, make sure we don't have any questions. You guys understanding what I'm saying there and kind of what our general gist is? Or does anybody have any questions? Okay. All right. We also have the sample size requirement. I'm going to come back to that. We'll do that at the end of this section. So let's pass on that for a second. All right. And what we can do when we go back to those red and green bars is we have this sentence that basically we're going to fill in. So we can say we are 95% confident that the interval from whatever our interval is, 0.49 to 0.51, actually does contain the true value of a population proportion P. So what that means is we're 95% confident that we got a red bar and it captures the true value of P and not a green bar. Okay. Now, let's get a little more scientific here and more exact when we're talking about this. So the first thing we have to do is talk about our critical value. Our critical value is just how far out we go. Okay, how many standard errors do we go out? Now let's think about this. The bigger the net, the more confident we are of catching the true proportion of P. The bigger the net, the more likely we're going to catch the fish. The smaller net, the less confident we are in catching the fish. Okay. How we adjust that is our confidence level. Okay. So in this first one, they want us to find the critical values, the alpha 2 for 90%. Okay, I've done this by hand here. I'm going to recommend doing it on StatCrunch, and I'll show you how to do that just in a second. So the lower the confidence level, the smaller the net, the less we got in either direction. The higher the confidence level, the bigger the net, and the further we have to go out in each one of these. Okay, so let's see how we find this value. So I'm going to pull up StatCrunch. And this is where we went in chapter 6, stat, calculators, and normal. We're going to go between. And what we're trying to do is this inner area is we're trying to force that to be 90%. So the way we do that in this bottom right box, we enter 90%. And what that does is defines that inner area to be 90%. Okay, so this 90% is this red area. And we're looking at how far we have to go in either direction. That's the 1.645. Okay, in either direction. So that's just saying we have to go 1.645 standard deviations in either direction. And that's what I have here by hand as well. Now, let's see what happens when we change that to 99.5%. So now we're very, very confident, 99.5% confident that we got one of the red bars. So now what we're going to need is a much bigger net because to increase the confidence, we have to have a bigger net. So let's see what happens when we do that. It's done the same way, but now we just put 99.5. So that pretty much makes everything red. And our cutoff is 2.8. So now instead of going out, what was it, 1.6 standard deviations, now we're going 2.8. And the reason why we're going more standard deviations in either direction is because we want a bigger net. The bigger the net, the more confident. So we can adjust the width of our interval just by changing the confidence. More confidence, the wider the net. Less confidence, the smaller the net. Okay, now hopefully, oh, sorry. So the question there was, will we always keep the mean 0 standard deviation of 1? Yes. So one of the reasons why we would do that is this is called a z alpha over 2. So z is always based on 0, 1. Okay, so yes, we'd always keep that at a mean of 0 standard deviation of 1. Okay. All right, so let's put all this together, and hopefully this will make sense in this number 13. So this number 13, it says in a study of the accuracy of fast food drive-through orders, McDonald's had 33 orders that were not accurate among 360 orders observed. Constructed 95% confidence interval for the proportion of orders that are not accurate. Okay, so we're interested in trying to figure out, what proportion of these McDonald's drive-through orders are actually inaccurate. Okay, so part A, it asks us, what the point estimate is. That's just taking the number of incorrect orders over the total we observed. Okay, so 33 over the 362. And that comes out 9%, or a little over 9%. Okay. So that's all we need to do for part A. Now, in this problem, we're going to break this problem up into multiple parts, but after this, we're going to do all this in one shebang. All right, so now that's our point estimate. Now we need to build a confidence interval around that. In this case, they want us to be 95% confident. Okay, so we can do that the same as we did before. I'm going to show you how to do this on StatCrunch in a minute as well. So to be 95% confident, we have to go out 1.96 standard deviations in either direction. That's our 2. Okay, that's what we keep calling 2. Is actually 1.96. Okay, this one you're going to probably look up enough that you'll remember this one. 95 is the most common one. So, that turns out to be 1.96. Right, so when we look at part B, if we want to find the margin of error, we have to find how many standard errors we go out. That's what we just did, the 1.96. And then we need to find our standard error. So that's the square root of p hat q hat over n. Let's figure out what that is. So we have p hat. That's the 9%. Okay. And then we have this q hat, the 0.9088. That's just what's left over from 1 because the p hat and q hat have to total 1. Okay, so q hat is just 1 minus p hat. So those will total 1. And then our n is the 362 for the number that we sampled. So we now have our point estimate, 0912, and we have our 2 standard errors in either direction, or 1.96 in this case. So now we got to take that point estimate and subtract our margin of error, and that's what our part C is doing. Okay, so our confidence interval is our point estimate, the 9%. We add and subtract the 2 standard deviations, and now we've just built one of those bars. We're not sure if it's a red or green bar, whether it actually captures the true value of P or not, but we're pretty confident, and that's what we do in part D. We set the confidence level at 95%, so we can say we're 95% confident that the interval from the 0.0615 to 1209 actually does contain the true value of the population proportion P. So again, what we're saying is we're pretty sure that we got one of those red bars. So let me redo this in StatCrunch to show you how that can help us. Okay, so remember our X is 33, our N is 362, and we want to be 95% confident. So this is a new place that we haven't been before. We're going to go under stat. We're talking about the proportions. We're talking about the proportions of errors in the McDonald's drive-through. So we're going to go stat, proportion stats, one sample, and then with summary. Okay, so that's something you'll definitely want to remember again. So stat, proportion stats, one sample with summary. So once we have that, we have to give it the data that they want. We had 33 successes out of the 362 observations. Now, the default is a hypothesis test. We'll do that when we get back from spring break. What we want is a confidence interval, so we click this other box of confidence interval. The default value is 95%, which is exactly what we're looking for, so we don't need to change that at all. And we hit compute. All right, so what we have is our lower and upper limits, and that's our confidence interval, the 0.0615 to the 12.08. I'm sorry, 0.1208. So those are our upper and lower limits, just like we found before. And our sample portion, this is our p hat. Okay, so that gives us our p hat and our confidence interval. So it does all the calculations behind the scenes. It figures out you have to go out, 1.96 standard errors in either direction, and it does it all for you. Okay. All right, any questions on that one? Okay, I have a video here using StatCrunch on a confidence interval problem, just like the one we just did. All right, so let's do another one that's very similar, just to make sure we understand what we're doing here. So this 18 says one of Mendel's famous genetic experiments yields 580 P's, 428 of green, 152 yellow, and we want to find a 99% confidence interval. All right, so we're of green P's. So we're interested in the greens. Okay, so we know we have 428 green out of the 580 total. So we find the ratio of those, which tells us that we had 73.79% green P's. Okay. So that's our point estimate. And now we have to add and subtract our number of margin of error. Now here we want to be 99% confident. So since we increased our confidence level, instead of 1.96, it's now 2.575. So we want to be more confident, so we have to go out further in either direction. Okay. You don't need to do this for this problem, but I'll show you how to find that value in StatCrunch. It's under calculators and normal, just as we did before. We go between, and that bottom right box, we enter in the 99%. Okay, so there's the 2.575. Okay. So then we take our point estimate, the 7379 plus or minus our 2.5 standard deviations, and we get this range from 0.69 to 0.78. All right, now let me reproduce that on StatCrunch. We're going to go to the same place. We're going to go under portion stats. We're trying to find the portion of green peas, one sample, and then with summary. Okay. So the number of successes we had, I don't remember now. Sorry. Let's see. We had 400. I can only write it down. So we got 428 green out of a total of 580. Okay, so let's try that again. Sorry about that. All right, so the number of successes is 428. The number of observations is 580. And we go down a confidence interval. In this case, we want a 99%, so we have to change the default from 95 to 99. When we hit compute, we automatically get our lower and upper limit of the 0.69 to 0.78. So it does all the calculations for us. Here's our sample portion as well, p hat. All right, now there's a follow-up question here. They kind of ask it in a weird way, but let's make sure we understand what they're asking. It says, based on his theory of genetics, Mendel expected 75% of the offspring peas would be green. Given the percentage of offspring P's is not 75%, do the results contradict Mendel's theory? Why or why not? All right, so when they say, given that the percentage of offspring P's is not 75%, they're referring to our point estimate. Okay, so we sampled these 580 P's, 428 of them were green, so it's 73.79%. They're saying that's not 75, so does that contradict his theory? Well, we really don't care what p hat is. What we care about is what our confidence interval is. So our confidence interval goes from 69% to 78%. That's what the proportion of the population proportion can fall anywhere in that range. So he was expecting 75%. 75% is certainly inside that range. So this little experiment he ran certainly, backs up his theory that it could be said that there's 75% would be green peas. So we don't want to look at the point estimate. We want to look at the confidence interval to figure out if 75% is there or not. All right, and then this last problem in this section is talking about our sample size requirement. Okay, so let me explain what they're trying to do, and then we'll look at this. So we've talked a little bit about how we can change the width of the interval based on confidence. The more confident we are, the wider the interval has to be. Again, bigger the net, more likely we are to catch the fish. The smaller the net, the less likely or less confident we are in catching the fish. Okay, so we can adjust the width of the interval by adjusting the confidence level. Another way of doing that is changing the sample size. Okay, so if we only have a few in our sample, 5 or 10, in our sample, the interval is going to be quite wide because you're not getting a good estimate to start with. Okay, so think about if you just, if I asked, how many of you guys smoke cigarettes, if none of you say you smoke cigarettes, then can we conclude that there's nobody that smokes cigarettes? No, it's just because we have a small sample. Okay? As we sample more and more people, we're going to get a better and better estimate. Okay? So as n increases, it slowly makes our interval more and more narrow. Eventually, if we sample everybody in the population, we have the exact value. So we start out quite wide, and we slowly can pinpoint, to the exact value if we sample everybody in the proportion, everybody in the population. Okay. So as an increase in the sample size or n increases, the width of the interval gets more precise. Okay. Now, if we set how wide we want our interval and what percentage, what confidence level we want. So in other words, we say, okay, we want it to be this wide and we want it to be 99% confident. We can calculate how many people we need to sample for that to happen. And that's what they're doing in this problem. Okay. So this is the thing I skipped over earlier. This here. And there's a couple things. If p hat and q hat are unknown, we use 0.5. That's the most conservative. And then we always round n up. Okay. So this is our critical value. So that's our value of 2 or whatever it may come out to be. Our p hat and q hat we've talked about, and then we have our margin of error. Okay. Once we calculate that, we have the sample size requirement. Right? So let's look at this problem and see how that works. Okay. So in this one, it says, in a study of government financial aid for college students, it becomes necessary to estimate the percentage of full-time college students who earn a bachelor's degree in 4 years or less. Find the sample size needed to estimate that percentage. Use a 0.05 margin of error and use a confidence level of 95%. Okay, so let's see what we have. So we want to be 95% confident and margin of error 0.05. So if we did this by hand, we can just plug this in, all right? So we want to be 95% confident. We've looked that up before. That comes out to be the 1.96. We know nothing about the percentage to be estimated. So we don't know anything about p hat or q hat. So we can use 0.5 for those. Okay, so again, if we don't know anything about p hat or q hat, we just enter in 0.5. And they tell us the margin of error is 0.05. So they throw that in the denominator and square it. If we do this calculation, it comes out 384.16. Right? Now, what I wrote down here is I rounded that up to 385. Let's make sure we understand that. So to have a confidence interval with a margin of error of 0.05 and to be 95% confident, we have to sample at least 384.16 people. Okay. The problem with that is we can't sample 0.16 of a person. You know, like the only way we can do that is like rip their arm off or something, and we don't really want to rip anybody's arm off. So we have to sample the whole person. Okay. So again, 384 is not enough. We need a whole nother person because we have that 0.16. So we have to take the whole nother person to get that 0.16. So we have to have 385. So let me show you how to do that on StatCrunch. We're going to go to a similar place. We're going to go stat. We're still talking about proportions. We still have one sample. And then our last portion spot, we go here to width sample size. Okay, so it's stat, portion stats, one sample, and then width sample size. All right, so the first thing is our confidence level, which is 95. Our target proportion, we don't know anything about p-hat, so we just use 0.5. So the first two defaults are good. Now here, they want us to enter in the width. And once we enter the width, they're going to give us a sample size. So let's think about this for a second. They tell us our margin of error is 0.05. So that's how far we go from our point estimate to one edge of our confidence interval. Okay. What we want is the width. So let's think about it this way. What the margin of error is the radius of our net, and what we're looking for is the diameter of our net. So even though they give us the radius, again, they need to find the width, so we have to double that margin of error. So if the margin of error case is 0.05, we need to double that to make it 10%. So in this bottom box, we put in 10%. When we get hit compute, we get that 385, just as we did before. All right. Now, part B is the exact same question. The only thing that's different is assume that prior studies have shown that about 40% of full-time students earn bachelor's degrees in 4 years or less. So they're telling us what p-hat is. So now we know what p-hat is, so we can enter in p-hat and q-hat appropriately. Okay. So if we do that, our target proportion is now 40%. And again, our width will still be 0.10. We compute, we get 369 there. All right, any questions on that one? Okay. So now we're going to go into section 7.2. Now 7.2 is very, very similar to the first section. The only difference now is instead of talking about proportions, we're talking about means. Okay. Same idea. We find our point estimate. We go our two standard errors in either direction to build a net, and we try to capture the population mean. Same idea. We're just we have a different formula because we're talking about mean versus proportion. Okay, it's the only difference. Now, before we get going, we have to talk about this new distribution called the t-distribution. Okay. So we're going to try to figure out, from this table, which distribution we're supposed to use. And one of the things we need to mention here is here we have sigma either known or unknown. So let's remind ourselves what sigma is. Remember, sigma is not only the standard deviation, but the population standard deviation. Okay. Very rarely do we know the population standard deviation, but that's what we're looking for, whether we have the population standard deviation or not. So let's see how this is done. So in this next two questions, it says, assume that we want to construct a confidence interval, do one of the following as appropriate. Find the critical t alpha over 2, z alpha over 2, or state that neither the normal nor the t distribution applies. Okay. So let's look at 7 and see what we have. So we have a confidence level of 99%. They tell us that sigma is $342,000, and the histogram is skewed, and they tell us that n is above 30. Okay. So if we go up here, they told us we know sigma. Sigma was 3,342. And they told us n is above or 30. So if we line up that row, that column, this is going to be a z. So this is nothing different than what we did in the previous section. Okay. So I'll remind us how to do that. Second here. Okay. So that's where we went under stat, calculator to normal. We went between, and between that red area in between, we wanted to be 99% confident. So we get to 2.575 or 2.576. All right, so that's where that comes from. So that's nothing new from what we did in the last section. Now let's look at 8 and see what changes here. So here are some summary statistics for randomly selected weights of newborn girls. We have n is 205. Our x bar is 30.4. Our standard deviation is 7.1, and we want to be 95% confident. Okay. Now, if we go up to our table here, we have n of 205, so that's obviously above 30. We have S, but we do not have sigma. We don't know anything about sigma, so that puts us in this last column, which is a t distribution rather than a z. Okay. So now we have something new that we have to talk about. All right, so let's see if I can find a little spot here to do a pretty little picture. All right, so we've talked about the normal distribution quite a bit, right? It looks something like that. Now, what a t distribution is, it looks very similar, but it's a little bit flat. Okay, so you got to use your imagination a little bit. So just pretend like somebody sat on the normal distribution, just kind of squash it down a little bit, right? So if somebody sat right on top of the normal distribution, it kind of squirt out the sides and kind of squish down. That's what a t distribution looks like. Okay, it's just a little heavier tails and so forth. Now the t distribution changes depending on our sample size. The larger the sample size, the more normal it is. The smaller sample size, the more sat on it is. Okay, so it changes depending on the sample size. Again, as the sample size goes up, it becomes more and more normal looking. Now, we have the same thing. We're trying to find 95% confidence. And we have something called degrees of freedom. Okay, degrees of freedom is just n minus 1. Okay, so in this case, we have an n of 205. So 205 minus 1 gives us a 204. And we can do this a number of ways. We can either use a table or we can use StatCrunch. I'll show you how to do both. So the degrees of freedom just tells us how sat on or unsat on this t distribution is. Does it look more normal or is it pretty sat on? Okay. So, before I go down, let me point out this. We want to be 95% confident. Okay, so that's the inner 95%, okay, in between our two bars. So if we have 95 in the inside, we have 0.025 in the outside. Okay, 5% total, split up evenly, 0.025 in either tail. All right, so we have this new table. Down this first column, we have degrees of freedom. And if we go down there, we're looking for 204. There is no 204, there's just 200. So we just go with whatever's closest. Okay, so that's where that part of it comes from. And then up top, we have the area in one tail or area in two tails. So that's just going back to what we have. We have a 95% confidence level, so we have 95 inside. So outside is 0.05, so the area in two tail would be 0.05, or area in either tail is 0.025. Doesn't matter if you look at area in one tail or two tails, it puts it in the same column. We just line up that row, that column, and we get to 1972, okay, which is circled there. Now I would recommend using StatCrunch, so let me show you how to do that. So this is going to be very similar. We're going to go under stat calculators, and now no longer distribution. We can't go to normal. We need to go to the t distribution because now we're using t rather than z. We have our degrees of freedom, which is n minus 1. So our n was, our sample size was 205. So our degrees of freedom would be 204. And then we go between. And that inner area, we want to be 95%. So it's very similar to the normal distribution. We just have to enter in the degrees of freedom as well. Now, I don't know if you guys remember or not, but when we did the normal distribution, going out, let's try it again. We use a normal distribution with a 95% confidence level. We had to go out 1.96 standard deviations in either direction, or standard errors. Here, when we're doing the t distribution, it's going to change depending on our degrees of freedom. In this case, it's 1.97. We have to go out a little bit further. Okay. That's going to change depending on our degrees of freedom. So say if we had 240 degrees or 2040 degrees of freedom and 95%, that's going to get very close to 1.96. But if we had 20 degrees of freedom, that's over 2. Okay, so it depends. That shows you how much it sat on just based on the sample size or degrees of freedom. Okay, so it does change in the t distribution. Okay, so now we have that. All right, now let's go to finding confidence intervals. Again, this is going to be very, very similar to before. Now we have two cases here. One where sigma is known, and one is where sigma is unknown. So let's talk about this first one. This is more of a theory-based deal. So we're trying to find the confidence interval for the population mean. And let's look at the assumptions. We have our samples in SRS, simple random sample. It has to be normally distributed or n is above 30. So remember back to chapter 6 with the central limit theorem, we had some crazy distribution. As long as we sampled enough, it became normal. Okay, that's what this second piece is doing. It's making sure it's normal. If it's normally distributed ahead of time, we're good. Or if it is a bit above 30, the distribution of the means will be normally distributed. And then this is where it falls apart, where the sigma is known. Okay, that's pretty rare. I have rare case. When I say rare, I've been in statistics for, I don't know, over 25 years, and I haven't seen it happen yet. So yeah, it's pretty rare. Let's figure out why. So what sigma is the population standard deviation. So the only way we can get the population standard deviation is to sample everybody in the population. And if we have everybody in the population, then we know what the population mean is. And if we know what the population mean is, then it would be really silly to estimate it because we have the exact value. So we would not want to do a confidence interval because we know the exact value. Okay. So that's where it falls apart, because if you have sigma, you have the population mean. If you have the population mean, you wouldn't want to do a confidence interval. So theory-based, this works very well, but not in practicality. We're not going to do any problems using this, and that's using that z distribution. When we go to the second one, sigma is unknown, and this is the case we'll be working with. We'll be using the t distribution. We have the same couple assumptions. We have to randomly select our participants, a simple random sample. And to satisfy the central limit theorem, we have to either have a normally distributed variable or n above 30. All right, so let's dive in and do one of these. So we're trying to construct the confidence interval for the estimate of the mean. This number 9 says here are summary statistics for randomly selected weights of newborn girls, and these are the same ones we looked at in the previous problem. We have the n is 205. It should be x bar here. Seeing that error. So that the mean of 30.4, the standard deviation is 7.1, and we want a 95% confidence interval. Okay, so this is very similar to what we did before. We take our point estimate, we add and subtract our 2 standard errors. We found that T alpha over 2 value in our previous problem. Okay, so we have to go out to 1.972. They told us our mean of 30.4. We add and subtract 1.972 standard errors. And it's the same setup as before. We're just using a different formula because we're talking about the mean rather than the proportion. So we again take our mean, add and subtract our 2 standard errors, and we get our range from 29.42 to 31.38. All right, so let's do this in StatCrunch. All right, now we're going to go under stat, and we have a bunch of choices here. Don't try to make this too difficult. What we do in this section is we're using our t-distribution. You'll notice that we have our t alpha over 2 value there. So if we're looking at, using a t-distribution, we have to go under t-stats. And one sample, in this case, with summary. And so we can enter that sample mean, which is 30.4. Our standard deviation is 7.1 and sample size of 205. And just like before, we don't want the hypothesis test. That's when we at our next class. And our confidence level was 95%. So we have to just click that box next to confidence interval for that. And we have our upper and lower limit of the 29.4 and the 31.37. Any questions on that one? Okay. Now we're going to do another problem very similar just to make sure we understand this. Or get another example of it at least. So this number 11 says data set 3 body temperatures of appendix B includes a sample of 106 body temperatures. So that's our N, having a mean of 98.2 and a standard deviation of 0.62. Construct a 95 and a 98% confidence interval estimate for the mean body temperature of the entire population. And then as there's a follow-up question, what does the result suggest about the common belief of 98.6 is the mean body temperature? All right, so I have these side by side. Again, we have the mean, we add and subtract our 2 standard errors. And the only difference between doing a 95% and a 98% confidence interval is just how far you go out. When it's 95, we have to go out 1.984. When it's 98, we got to go 2.364. It's just how wide is our interval. The wider the interval, the more confident we are. The smaller the interval, the less confident we are. Okay, so that's all we're changing. All right, so let me pull this up in StatCrunch. Same place, stat, t-stats, one sample with summary. So our sample mean was 98.2. Our sample standard deviation was 0.62, and our sample size is 106. And the first one they want us to do is a 95%. So we can click confidence interval. And here's our lower and upper limit. Okay. So, growing up, our mom always told us that the mean body temperature was 98.6. What do we think after we see this? Here's our 95% confidence level between 98.08 and 98.31. Well, 98.6 is outside that range. So this is shows evidence that when our mom told us that the mean body temperature is 98.6, that she was lying to us. I don't think we want to tell our mom that she was wrong, but I think she was. Now let's, go back and instead of 95, let's do a 98% just to make sure that we're even more confident that our mom was wrong. And here, the limit goes from 98.05 to 98.34. Again, 98.6 is still not in there, so it's even stronger evidence that our mom was wrong. Okay, again, I wouldn't recommend telling her that, but that's looking that way. All right, questions on either one of those? Okay. Now, this next problem is something that entered into my personal life, and I want to show you how using these confidence intervals can help with problems that we do see. Okay, so I talked a little bit about a fish survey that my friends and I did in California, a few years ago. Um, One of the fish we were catching was these lingcod. That's my little guy with a pretty big lingcod. Obviously, they get pretty good size. Um, and we're do a lot of fishing out there, and we're concerned about the mercury levels of these fish because they're obviously get big, but they're very predatory type fish. You can obviously see they have a big old head, and they'll eat anything. A squid swims by, they'll eat a squid. Crab walks by, they'll eat a crab. Fish swims by, they'll eat a fish. Whatever they can eat, they're going to eat. In fact, quite often the way you catch them is you catch another fish, a smaller fish, and as after you hook that, the lingcod will see that that fish is in distress, swim over and eat the fish that you just caught. So when you reel it up, you actually have the fish you caught inside the mouth of the lingcod. So you kind of do a 2-for-1. Um, yeah, exactly. It's pretty neat. Yeah. So the problem with this is when these bigger fish, get big, over their lifetime, they've eaten a lot of fish. And each time they eat a fish or a squid or whatever it may be, they take in just a little bit of mercury, and a little bit of mercury, and a little bit of mercury. And, if it's a small fish or, they grow fast, that's fine. But when you get a bigger fish or they live longer, then mercury can be a problem. Okay. So we were able to get a grant to actually study this. And basically, this is the question. I've made it a little more formal than what we're actually trying to do. But the published paper doesn't have this, but it was more. This is more of my personal spin on it. And what I want to know, I have there is the Office of Environmental Health Hazard, OSHA, do not consume levels for methylmercury is 0.44 parts per million for women under 45 and children. Construct a 90% confidence interval for those levels of methylmercury and lingcod. Should women under 45 and children be eating lingcod? So basically, each group of people has different tolerances for methylmercury. Males, for instance, have a little bit higher tolerance for methylmercury than females. I don't know why. Younger women have less tolerance than older women. I don't know why. But, I'm not only eating these fish myself, but I'm feeding it to my woman and my child. So, yes, I'm interested in the woman that's under 45 and the child, and making sure that we're not over this 0.44 parts per million when, we catch a fish as this one and bring it home. Okay. So we did this study, and here we have the methylmercury levels of the fish that we caught. Okay. Now I have a note there that the sample size is only 18. Now, one of the assumptions is the data has to be normally distributed or the sample size has to be above 30. Now, I'm stretching this a little bit. This is somewhat normally distributed, which is probably good enough, but barely. And, like I'm on the red line here. I mean, I would like to have a larger end. Okay. But this is the kind of things that you run into when you're in real life. We're getting paid to do this survey. Yeah, we're going, get paid to go fishing, right? Not too bad. And there's not an unlimited amount of money. So, what we got paid and what, was allowed was, catching, these 18. Ideally I would have caught, 2 or 3 times that much and get better, more precise results, but that's just the way it works. Okay. Money takes over. Now, we have all these methylmercury levels. And so what's different about this problem than the previous ones is before they had it all summarized. We were talking about 106 body temperatures with a mean of 98.2 and a standard deviation or whatever it was. when you do this in real life, you don't automatically have the mean and standard deviation. These fish don't, come up and calculate that for you on the way up. You just have to, take your methylmercury and do that yourself. So let's see how we handle that. So I've entered all these methylmercury values in the first row. When you get to your homework or quiz questions, you can copy and paste it in there, or open up in StatCrunch. And we do it very similar. We go under stat, T-stats, and one sample. But now we don't have summary, we have the raw data. So we go with data instead of with summary. We can select our methylmercury, and then we can do our confidence level. I think I wanted 90% in this case. And then we can hit compute. Okay. So we get our lower and upper limits. I've already got all this in the notes, so I'm going to switch back to the notes here, but that's what we have. So that's all here. So here's our lower and upper limits. So what we're interested in is, do these Lingcod have methylmercury levels that are higher than 0.44 parts per million? Because 0.44 parts per million, women and children are not supposed to eat it at all. Okay, so we've got this confidence level from 0.46 to 1.06 parts per million. So let's think about that. Even our lower limit is above 0.44 parts per million. And we're 90% confident that the true value is somewhere between 0.46 and 1.06. So we're very confident that the true value of the true mean for the methylmercury is above what women and children should be eating. Okay, so what I said right down here before: should women under 45 and children be eating Lingcod based on OSHA's do not consume levels set at 0.44 parts per million? And the answer is no, because the interval suggests the level of methylmercury is above that. Okay, so the lower limit is above what they say do not eat. The upper limit's 2.5 times more than what they should eat. So these fish are they're loaded with methylmercury. Okay. So I wanted to introduce that, just kind of as a problem that, entered into my life. I obviously learned that, these vague Lingcod are not going to be brought home to my woman or my child. So I think that's good information. Okay. All right. And then this last problem, this is doing our sample size requirement. So that's, if we want to set a width for our interval and we want a certain confidence level, how many fish or whatever do we have to sample to figure that out? Okay. So one of the problems, let me go back to this fish example. Notice that these lower and upper limits have quite a wide range from 0.46 to 1.06. That's a pretty big interval. And the reason why that interval is so big is because we only have 18 fish. If we had 50 fish, it would be smaller. If we had 500 fish, it'd be very small. So as we would catch more and more fish, we could, get that average methylmercury level, much more precise. So, the problem with that is it costs money. And that's why we didn't do more, because we were getting, paid for this. And, if we, to be able to catch more than 18 and do this methylmercury sampling and all that, we would have needed more money. Okay, and that's what happens. So this 30 is basically saying, okay, if we wanted to find, a more precise methylmercury level on Lingcod, how many do we have to sample to be tighter? Okay, they're not using the methylmercury, but same idea. So this 30 says, assume that sigma is equal to 15 for the IQ scores. Attorneys are grouped with IQ scores that vary less than the IQ scores for the general population. Find the sample size needed to estimate the mean IQ of attorneys, given that we want to be 98% confident that the sample mean is within 3 IQ points of the population mean. All right. So we have a new formula here because now we're talking about the mean and not the proportion. So we had what level? We want to be 98% confident. Okay. So that's our Z alpha 2. So we'd have to got 2.33 standard errors in either direction. They told us sigma is 15. They told us the margin of error is 3. Okay. Again, like before, whatever this comes out to be, we have to round it up. And notice that here we're using Z and not T. Okay. So let's show you how to do that on StatCrunch. We're going to go under stat. Instead of T stats, we're going to go under Z stats because they have the Z in the formula, not the T. We got one sample and then with sample size. Okay. So our confidence level, we wanted to be 98%. They told us our standard deviation was 15, and our width is 6. Okay, let's figure out why we got 6. They told us our margin of error is 3, so that's from our point estimate to one side of our net and our point estimate to the other side of the net. So they're giving us a radius of 3. We want the diameter of 6. And if we hit the sample size, we get, what did we just do? All right, I did not mean to do that. All right, we get the 136, okay, which is what we found before. All right, so let me stop there and see if you guys have any questions. All right, so that's chapter 7. It's what's the question? So you get the width. We don't square the margin of error, we double the margin of error. Okay, so our margin of error goes from our, just asking how you get the width. So the margin of error goes from our point estimate to one side of our net. So if that's 3 and we go from the point estimate to the other side of the net, that's also 3. That means our width is a 3 plus 3 or 6. Does that help? Okay, is it, anybody else have any other questions? Okay, so we're right back on our Tuesday schedule here for a while. Next week we have spring break, so the chapter 7 stuff will be due in 2 weeks. If you have not yet looked at the chapter 6 stuff, I would do that soon. Certainly, if you have any questions or anything, please get in touch with me, and I will certainly help you out the best I can. If you feel confident, you can go ahead and drop off. If you have any questions or anything, please stick around and I'll answer any questions that you may have.